it's a pretty easy find. So.
I'm going to Walmart today. If I find it, I'll take a picture and email it to you.
Okay. All right.
That's a really good question, but time already
Oh,
started.
then my announcement slide didn't sync. I don't know what's going on.
I'll have to say it's my...
Okay, well, all right, hold on. My announcement slide didn't sync. I don't know why.
We all get 100% on our exams?
Nope.
No? That's the math thing.
Well, I'll just do this.
That'll take all of that. I mean,
I don't know. Yeah, it didn't sync for some reason. I don't know why. Okay, because I had it ready to go. Oh, well. Okay, everybody, let's get started. I'm still working on grading the second exam, so but I'm still working that out. As you could probably guess, it's a hectic week for registration. So I am mostly interested in how we talked a little bit about it before class started. But how did homework 8.1 go? Was that pretty smooth? Okay, good. I want to be clear on the topic for today. So when we drew influence lines for reactions, and maybe what I ought to do is just jump right into the to the slides. Did everybody get the code? Everybody get the code? Let me jump right into the slides because I think I don't want to take away from this topic too much because essentially the whole thing about today is I presented to you a set of rules for influence lines for reactions. And now I'm going to present you a different set of rules for determining internal shears and moments. The rules make sense when you're thinking about internal shears and moments, but they are different than a little bit different than the rules for reactions. So I want to make sure we've got the context in mind. So first off, let's just make sure that we're all clear about the base definition for an influence line. Now, just like last time, we're going to try and divert to the Mueller-Breslau principle, but just remember the idea behind an influence line is that it is the record of a given response when you move a unit load across the structure. So you pick a point of interest, you move a load across the structure, and you record that response. Okay? And I do want you to keep that in the back of your head. Now, that is a very nice theoretical underpinning, and it is a very nice gut check for the construction of an influence line. It's how we would do things like the influence line for a given reaction equals 1 at that reaction and 0 at all other reactions, right? Because that's what you're doing. You're moving the load. So that was sort of a way that we developed that rule. But ultimately, we were using the Mueller-Breslau principle to construct the influence line. And so what do we do with the Mueller-Breslau principle? We remove from the structure the ability to resist whatever response we're looking at, and we move the structure through a unit deformation. Now, in the case of reactions, what we were doing is we were taking a structure and we were saying, okay, let's take this structure and remove this roller, or remove that roller, or remove that roller, etc., and move it through a unit displacement, okay? So I got a little Desmos friendly the other day, and even this morning. I posted a link to this, so you all can mess with this if you want. But I'll show you something. So the way it works is if you look over here on the left, there's this thing called scaling constants. And so the way a scaling constant works on this graph is, so for example, if you say CA, and I take CA and I do that, what it does is it plots the influence line. And so this is, CB, etc. But just to sort of walk through what we're doing here, so this is support A, this is support B, this is support C. So let's consider the influence line for the reaction at, let's say, C, okay? So what do? We would remove this support, okay? So if you want, you could get kind of fancy with it. We could say, okay, let's remove that support. So that support's gone. And then we're going to move this through a unit displacement. But see, we have a hinge right here. So if I take this point and I pick it up 1, okay, what's going to happen is it's just going to do that, right? And so that's the influence line for the reaction at C, okay? Likewise, if I say, okay, let's remove support B, okay? So if I remove support B, okay, what's happening is I'm going to take this point and lift it up 1. But keep in mind, it's still pinned here, and it's still pinned here, and here's my hinge, right? So what's happening is, with support B, what's happening is that hinge is where it's changing location. Okay, does everybody see that? Okay. And then with A, you know, we're just pivoting around that reaction. Okay. All right. So, so that's fine for the construction of influence lines for reactions. Okay. And there were rules that we developed for influence lines for reactions. We know that they equal 1 at the reaction of interest and 0 at all other reactions. We know they're linear, and we know whenever we have a hinge, it serves to change the slope of the influence line. Okay? That's fine for reactions. For shears and moments, those rules are slightly different. Okay? So let's talk about influence lines for shears and moments. Okay? So like I said, one of the, I guess, the key drawback, or one of the drawbacks for an influence line, is you cannot draw an influence line for a shear and moment everywhere along the beam. And that's the inverse of what happens with a shear and moment diagram. See, when we plot a shear and moment diagram, what we're plotting is the change in shear and moment across the entire structure. So when you look at a shear and moment diagram, and you know, here's the beam, the value here is the shear here, the value here is the shear here, and so on and so forth. So it's a continuous plot of the shears, a continuous plot of the moments across the entire structure. That doesn't work with an influence line. With an influence line, what you're recording is the load's position everywhere, but your point of interest remains fixed. So whenever you draw an influence line for shear or moment, it is the response at a given point, or the response at a given point, okay? So when you draw an influence line, it's the influence line for the shear here, or the moment here. So you keep your eye fixed on that point as the load moves across the structure, okay? But the idea is the same, okay? The theoretical underpinning, we're moving a load across the structure, moving a load across the structure, etc. Now before I show you this, let's have like a little bit of a thought experiment here, okay? If I put a load right there on top of A, what is the shear here? Think about it like this, okay? So imagine I've got a table and I'm sitting right on top of the leg of the table. How much bending or shear is the table saying? Nothing, right? Okay? So if I'm drawing an influence line for shear and moment, I'm already thinking of a different rule. Whenever I draw an influence line for shear or an influence line for moment, would a fair statement be that it has to equal 0 at all reactions? I mean, is the beam seeing any shear or any bending if the load's right here? No, right? Okay. All right, so that theoretical idea is in the background. This is what they look like, and then we'll talk a little bit later about how to construct them. So whenever you draw the influence line for shear, it sort of looks something like this, okay? What happens is you have this jump, this tendency to jump downward on the left, and this tendency to jump upward on the right. And then for moments, you have a tendency to rotate this way on the left and this way on the right. Okay? Now, why does it go like that? Why this direction? Why this sign convention? Because what we're doing is mimicking the internal sign convention that we've been using this whole semester. For example, okay, if I have a beam, okay, and I cut a section with the samurai sword or lightsaber and I split it up like this, if I look over here, what's positive shear? What have I been saying positive shear is? If I cut a section and look to the left, positive shear is, I'm waiting, down. Upward shear up here is positive. This is positive shear. So cutting a section looking to the left, downward shear is positive. Cutting a section looking to the right, upward shear is positive. Well, if we look at our influence line at our point of interest, we're tending downward on the left, upward on the right. Is everybody seeing that? It's sort of doing that. Okay? Now, I'm using some very specific language here. I'm not saying that it always goes down on the left and always goes up on the right. What I'm saying is it's tending downward on the left, tending upward on the right. And the reason I'm being a little wary with my verbiage there is because of cantilever beams and fixed supports, which we're going to talk about on Friday. So for now, I guess you can sort of think that this is going to go down and this is going to go up, but recognize come Friday, that's going to change. Now, in the case of moments, what's happening, if I look at my positive sign convention for moments, okay, my positive sign convention for moments says that is a positive moment and that is a positive moment. Make sense? So, what we're doing when we look at moments is we're sort of rotating up like that, and what's happening is a rotation up like that, okay? Now, right now we're just thinking qualitatively, okay? But I guess the key thing I want you to see is generally what does the shape look like at the response of interest, and then the other thing I want you to see on this slide is 0 here, 0 here, 0 here, 0 here. Why? Because the internal response in a structure, if a load is directly over the point of, over the reaction, if a load's on the reaction, the structure's not seeing anything. Okay? Make sense? Okay. All right. Now, this is a little bit of food for thought that we're going to talk about next week. But one thing, again, I've been saying that one of the drawbacks of an influence line is that you cannot, like, you have to pick a point of interest, right? So this is the influence line for the shear here. If I draw an influence line for the shear here, I'm going to get a different influence line. So one question you might ask is, how many is enough? Okay. Well, later on, we're going to learn how to use influence lines to generate moment, what we call moment and shear envelopes. That's what you need for bridge design. But if the question is how much is enough, a common practice in bridge engineering is to draw an influence line at every 10th point along the span. So if a bridge is 50 foot long, draw one at 5 foot, 10 foot, 15, 20, 25, 30, 35, 40. Does that make sense? Most software packages will automatically do that at 10 points. You can do more. Some states may require more and whatnot, but 10 is usually enough. And honestly, if you can do one, you can do as many as you need. So we're going to talk about that next week. Okay. So some sign conventions. Here I am stealing my own thunder. So what we're doing, positive shears, internal goes down, left side goes down, right side goes up, moments, that way and that way. Okay. So let's take them one step at a time. Okay. So let's talk about influence lines for internal shears. So let's go back to the Mueller-Breslau principle. What do? Okay. What does the rule say? We pick a point of interest. Well, we've done that right here. Okay. We remove from the structure the ability to resist that response. So in that case, what we're doing is we're removing from the structure the ability to resist shear right there. So if I'm looking at this structure, what we're essentially doing right here is we install what's called a shear release. Okay? So we basically put this sort of release in the structure right there that prevents the structure from resisting shear right there. Now, it can't resist shear, but it theoretically could resist axial loads or moments or so on and so forth. Okay? Now, what we would then do is we would take that structure and we would put it through a unit displacement. Okay? So here's my shear release. Okay? We remove from the structure the ability to resist shear at a point of interest. And then what we do is we put it through a unit displacement. Okay? So what does that mean? Well, we're going to sort of tend the left side downward and the right side upward. Okay? So what's going to happen is the left side is going to go down, the right side is going to go up. So if I'm still pinned right here and the left side's going down, it's going to kind of like do this whole thing. Okay? And if the right side goes up, what's happening is the right side is going up. But keep in mind, it's pinned down here, and I got a hinge. So here, we've got this sort of like seesaw thing going on around the central roller, and then we got a hinge here that pivots us back up. And that's what the influence line looks like. And just to sort of make the point, I did my little animation right here. I knew there was a reason for this, so I've got this right here. I've got my little point of interest right here, this little purple point right here. Let's say I install a shear release. I install the shear release, and you can see what it's doing. Does that make sense? How the left side's going down, right side's going up, and then, you know, it's pivoting around the supports and then that hinge serves to change the direction. Does that make sense? Okay. Now, one of the, I guess, quirks of a shear release is that it is just that. It is a shear release and nothing else. Okay? And so the way that mechanistically that will work is, so let's go through a couple things. So first off, we're moving it through a unit displacement. So what does that mean? I want a total displacement right here of 1. So if I do a little bit of geometry right here, what I'm saying is that this total displacement is 1. So when we construct an influence line, what we're going to be interested in is figuring out what is H1, what is H2. Well, I don't know what H1 and H2 is, but I propose the sum of them is 1. Everybody okay with that? Now, like I said, it's a shear release, it's not a moment release. So the way that we constrain this from only releasing shear and not moment is that this line and this line have to have the same slope, okay? So if this line and this line have to have the same slope, how do we get the slope of this line? Rise over run, so H1 over L1, rise over run, H2 and L2, H2 and L2. Send that over, and we can solve. And you don't have to get super worried about writing down these expressions, because you'll see when we start doing a problem, you'll see how we can sort of naturally come up with these, and it's really not that bad. A little bit of algebra, but once you get this, it's pretty straightforward. Ultimately, what you just need to keep in mind with a shear influence line, total jump is 1, and that line is the same slope. Okay? Everybody okay with this? All right, now let's look at moments. Okay? For moment influence lines, what we're going to do is we're going to remove from the structure the ability to resist moment. So let me ask you a question. If I have a structure and I want to pick a point and say I don't want that point to be able to resist any moment, what should I put at that point? Like, what should I put here to prevent the structure from being able to resist moment? A hinge, exactly right. So I will put a hinge right there, okay? So I remove from the structure the ability to resist moment, so I stick a hinge right here, okay? Then what do? I take the point and I move it through a unit displacement. But in the case of moments, I'm not interested in a unit displacement as much as I am a unit rotation, okay? Now, we have used the term rotation and slope interchangeably. So how does that work? Okay. Well, I'll show you over here and I'll show you here. But in the case of moments, we're sort of doing this. Okay. So we're going to pick this point up some. So keep in mind we're pinned here, pinned here, pinned here. So we're going to rotate this side up, rotate this side up, and we're basically going to pick this point up. So we're going to pick it up like that. Then over here, it's going to seesaw around this. There's a hinge, brings us back up, okay? And that's going to be what the influence line looks like, okay? Now, how do we actually get values? Or more specifically, what do I mean by a unit rotation? What I'm saying is that this total angle change right here, this total angle change needs to be 1. And how do I figure that out? Well, it's actually pretty easy. How do you figure out the slope of that line? What's the slope of that line? Well, it's whatever that height is divided by, we'll call that L1 and L2. It's whatever that is, right? And then this is whatever that rise is divided by whatever that run is. And I propose that the sum of these must equal 1. Does that make sense? So we take it, we rotate it up, we move it through a unit rotation, we get a height, an L1 and an L2, and again, I'm just saying that the total slope has to equal 1, okay? So we'll say rise over run, and then now all you have to do is just plug this in and solve for H, and you've got the influence line figured out, okay? And again, does this match like what we would expect if we were to animate this thing? Well, let's see. If we have the structure pin, already a hinge here, stick another hinge there, got a solid segment, stick a hinge at our point of interest, and that's what it's going to do. Does that make sense? took a lot of work to do. And if you want to even watch this, so I even like, just saying. I just think that's cool. Okay. So, in case you want a hashtag Instagrammable slide, I put them all on the same slide. You know, here's going to be my fundamental expression for computing shear influence lines. Here's my fundamental expression for computing moment influence lines. Here's our schematics, and then here's going to be the rules. And these rules are just a little bit different than the rules for reactions. What's the same? Like, what's the same between influence lines for reactions and influence lines for shear and moment diagrams? Well, they are linear. They are lines. So that's the first thing that's common. The second thing that's common is that if there's an internal hinge, it'll change the slope of the influence line. What's different is this rule, okay? When you draw an influence line for reactions, they equal 1 at the reaction of interest, 0 at all other reactions. But when you're drawing an influence line for shears and moments, they are 0 at every reaction, okay? Does that make sense?
What does it mean for a slide to be hashtag Instagrammable?
It means that I'm a dork. That's what it means. Like, comment, and subscribe. This video is brought to you by Raid Shadow Legends there. I really enjoy my Factor meal subscription. I love my job. I'm glad you took the technical content from my lecture.
The next lecture brought to you by Squarespace.
Squarespace. We just need to start listing the ones, the common ones.
Yeah.
So, all right, everybody, it just makes sense? Okay, so now what I want to do is I want to go back to the lectures, the problems that we did last time, and I want to construct internal influence lines for shears and moments. Okay, so what we're going to do is we're going to go back to these problems, and we're going to essentially, I don't want to say do them again, but we're going to take the same structures and look at them a little bit differently. So I want to take this beam, copy, paste. You could put it, you know, right there. I'm just being kind of lazy here. I'll just draw them again. Okay. So what we're going to do is we're going to draw influence lines for shears and moments. For this one, we're going to draw them at point B. The textbook will say either at a point or at a section, so that's why these two examples have both of those notations. I think in practice I usually say like a section, but that's just me. Like section 1-1 or section 1-2. Actually, usually what I'll do is say like 0.1L or 0.2L or something like that. That's what the bridge engineer in me does. Okay, so let's draw our influence line for shear first. And then we'll do the influence line for moment. Okay. And I'm going to sort of do this just to separate all the calculations we did last time from the calculations I'm about to do. Okay. So let's make sure we've been paying attention. What is going to be the value of these influence lines at A? What about at C? 0. At the reactions, the influence lines are 0. Okay? So for both of these, 0, 0, 0, and 0. Okay, I'll put the labels up here. Okay. All right, so let's do shear first. Okay? So let's first off see if we can construct it graphically. Okay? So what we're going to be doing is installing a shear release in the beam right here. Okay? And so we're going to be deforming the beam such that the left side goes down, the right side goes up. But we also want to do it in a fashion where these two lines have the same slope, okay? So I'm going to do my best here. Let's see what I can do. Maybe something about like that. I think that's probably pretty good. Okay. Now, a couple things I do want to point out. From B to D, this is all one solid segment of the beam, okay? So the influence line doesn't just stop over here. Like this, we're rotating that entire beam segment about point C, so the influence line just keeps on going, okay? Okay. Does that make sense? Okay. All right, so let's put some values on this. So what I'm going to do is I'm going to call this H1. Call that H2, that height. We'll do this in absolute values right now, even though, like, so I know this is going to be a negative number, but let's just get our magnitudes to make this easy. Okay? So, okay, I'm going to redo that. Whoever that is, they're going to have to wait. Okay. Okay, so let's look at our shears. So how do we get height 1 and height 2? Okay, so the first thing that I need to figure out is, or I need to recognize, is that what is the sum of those two heights have to be? What does the sum have to be? 1. Okay? Okay. So that's the first fact that is true. Oh, 1, not H1. 1. So we'll call this equation 1. Okay? What is the second thing that we know that is true? We know that this line and this line are at the same slope. Okay? So what is the slope of this line? How would we calculate that? Rise over run. H1 over what? 20. So would you agree that H1 over 20 equals H2 over 10? Is that a fair statement? Okay, so this is equation 2. So all this is solving two equations. That's all this is. Okay, so what we're going to do is, let's take equation 2. So would you agree that if I cross-multiplied, or maybe did it like this, would you agree that H1 is 20 over 10 H2, or 2H2? Would you agree with that? And all I'm doing is just taking the 20 and multiplying it over. Is that okay? If I went too fast on that, you let me know. Did I have a boo-boo? Did I do it right? Okay. Did I get it right? Did I get it right?
Yes.
Okay.
Oh, yeah, I'm just kidding.
No.
Wait, so why is it H1 over 20 and H2 over 10?
So what I'm saying is the slope of this line. It's like, how do you calculate the slope of this line? It's the rise over the run, and the run's 20. This line right here is the rise over the run, and the run's 10. Does that make sense?
Thank you.
No problem, no problem. Okay, now, what I'm going to do here, here's what I'm going to do here. So, if I go back to equation 1, H1 plus H2 is 1, I'm going to replace this with 2H2. And I'm going to say 2H2 plus H2 is 1, so 3H2 is 1, therefore H2 is a third. And if H2 is a third, what's H1?
2/3.
2/3. So in terms of values on the influence line, it's going to make this negative 2/3. It's going to make that positive 1/3. What is this value right here, by the way? What's that value? If this is positive 1/3, that's 0, that's 10 foot, that's 10 foot, what's that? Negative 1/3. And that, ladies and gentlemen, is the influence line for the shear at B. Does that make sense? I'm hoping that's not bad. I'm hoping that's smooth. Everybody okay with that? All right, let's do the moments now. Okay? So I'm going to erase all this up here. Okay? So for the moments, what do I install here at point B?
Hinge.
A hinge. So I'm going to install a hinge right here. And then I'm going to deform it by rotating this point essentially up like that, okay? And I'm going to rotate it such that I have a total rotation of 1, okay? So that rotation, what it's going to do is I'm going to pick this point up some. So I think constructing the shape of the influence line is probably pretty easy. But the hard part is figuring out what this height is. We got to figure out what that is. Okay. So how do we do that? How do we do that? Well, see if we can figure that out. We are moving this through a unit rotation, right? A unit rotation. So we have an angle here and an angle here. We have this angle and that angle. What do we know about the sum of those angles? 1. Now, we're using small angle theory here. So in small angle theory, we can just represent that as rise over run. Okay? So what is the rise over run of this line right here? This line. H over 20. Okay? What's the rise over run of this line?
H over 10.
H over 10. So now this just becomes a fractions problem, okay? So what I'm going to do is I'm going to say this is H over 20 plus 2H over 20 equals 1. So H over 20 plus 2H over 20 is 3H over 20. So H is 20/3. So this is 6.67. And if this is 6.67, what's that value? Boom. Okay. Does this make sense? I'm hoping this is doable. Don't worry, we're about to do another one that's a little tricky here in a bit. But I want to have a discussion about applications. Okay? So, it doesn't really matter which influence line we take, but we can identify some interesting features here. Okay? So what does the beam originally look like? What's the beam look like for this problem? I mean, ignore all the hinges and the releases that we put in. This is what the beam looks like. It's a beam with a roller and that, right? And our point of interest is like right there. Is that fair? Okay. I want you to think about loads. Let's think about a distributed load. Let's think about like just some distributed load. All right? Now think about what that distributed load would be simulating if we were designing a bridge. That distributed load would probably be like the stream of cars on a bridge, right? Okay? Now let's say we're designing like a really long bridge. Does the traffic on the interstate consist of a steady stream of perfectly evenly spaced cars from beginning to end every segment of the interstate, or do cars on the interstate occur in clumps? Like you're driving down the road, there's a heavy traffic region, there's a low traffic region, etc. Right? So if I'm designing a beam, right, I could have some of that distributed load right here. I could have distributed load right here. I could have distributed load right here. Like I could, almost as if that was a bucket of paint, I could put the segments of that distributed load wherever I want, right? And it could simulate traffic on the bridge. So let me ask you a question. What's the worst case? Okay? So let's take moment, for example. Where do I put, like if I have, this is my distributed load. Where do I put that load to generate worst case moments at this point? Well, we have two cases. We have two options. Okay? I propose that to generate the worst case positive moment, I'm going to put that distributed load here. And to generate worst case negative moment, I'm going to put that distributed load there. How did I come up with that? That's my influence line. I propose that if I want to generate the worst case positive moment, I put the moment everywhere there's positive values, or put the load everywhere there's positive values on the influence line. Anywhere there's negative values on the influence line, put it over here. This is the, if this is my load, I propose this is the worst case placement for positive bending moment. This is the worst case placement for negative bending moment for this point of interest. Does that make sense? So we will use this later to derive moment and shear envelopes. It's just an idea I want in the back of your head for later. Okay. Everybody good so far? Did constructing these influence lines make sense? That's what I'm really interested in your ability to do right now, is just make the things. Everybody good? Let's do one that's a little trickier. Let's do this one. Oh, I just want the beam. Come on. Oh my goodness. Okay, well, actually that's probably a little serendipitous because I can just, okay, we'll just do that. Okay, so here's the beam, and we're going to draw the influence line for shear and moment at that section. Actually, hold on, we'll move that one up. Okay. So let's see what we can come up with here. Let me move this microphone. Okay. So let's do shear in moment. Give me some points that I should indicate right now before I draw any lines. What are some values that I know right now without drawing any lines?
0 to support.
0 where?
At the supports.
At the supports. Okay. So 0, 0, 0, 0, 0, 0. Right there. Okay. We know that's the case. All right. So let's do shear first. So we're going to install a shear release right here. Install a shear release right here. Somebody tell me what the shear influence line looks like. Tell me what it looks like, let's say, from each segment. Who's a volunteer? Go ahead.
Oh, no, I was still thinking about it.
Oh, it's okay, it's okay. Anybody got an idea for me? Tell me what happens here. What's the deformation look like? What's the left side do? Here's my release. What happens to the left side? Does it go up or down?
Down.
Right side?
Up.
Okay, so let's do the right side first. What's the influence line look like over here? So it's going to be up. What's it going to do?
Go down to 0.
Just go down to 0. Okay? Over here, this is all going to be a solid segment, right? So it's going to pivot around this, right? Then we've got a hinge that's going to bring us back. And what can you tell me about these two lines right here? Their slopes are the same. So let's see if I can make this neat. Is that my influence line right there? And we know that this influence line, or that line and that line have the same slope. Is that okay? You all have pencils or tablets or pads. I'm going to give you a minute. I want you to see if you can tell me what these heights are. I want to put you all to work for a minute. I'm going to enjoy my carbonated water.
This
irritates Mr. McCoy.
It does, especially ordered from Sweden, probably. Sparkling.
Iceland.
Iceland, my
I
bad.
knew it, bro. I told you. I didn't say you did.
I knew it was this original. That's what he's working.
I just picked it up and she
Out of all the options that she, you got carbonated water.
I like it. I like my liquid static.
You could just get like a pop or something. This thing's not this chocolate. Be static.
What my wife says, should taste like static.
It does. That's what like Sprite is static with the taste.
But liqueur has like there's lemon flavor. There's
Lemon flavored tea.
oh my lord. All right.
Sure.
I'm curious. So keep going. I want whoever gets there first. I want you to tell me what these heights are.
Oh, so the race?
Yeah.
That's like,
Yeah. All right. Hold on. We got an answer. What we got?
Bottom is -0.7 and top is 0.3.
That is correct. That is absolutely correct. So how do we get that? How do we get that? So we know that H1 plus H2 is 1. Okay? So that's H2. This is here. I'll move this. This is H1. And we also know that H1 over 14 is H2 over 6. So it doesn't really matter how you do it, but what I did is I said, therefore, H2 is 6 over 14 H1. So therefore, H1 plus 6 over 14 H1 is 1. So this is 14 over 14. This is 6 over 14. So that's 20 over 14. H1 is 1. 20 over 14 is the same as 10 over 7. Or H1 is 14 over 20, which is 7 over 10. Does that make sense? Is everybody getting that now? So that makes this negative 0.7. This is 0, this is 0, this is 0. Does anybody know what this is? This is easy because if we have 0.7 is to, so how do we get, how do we do this? We say 0.7 is to 14, so we'll say 0.7 is to 14, we'll call this H hinge, as H hinge is to 8. Does everybody see that? So I'm basically saying this rise over run has to equal that rise over 1. So what is that going to be in that case?
0.4.
0.4. Does that make sense? It's not too bad, is it? Yeah, so we just say this line is the same slope, so if we know rise over run here, we know rise over run there, we can solve for that. All right, I'm going to knock out the moment one real quick. So we have a hinge here. We rotate up, so we're going to have a pretty straightforward influence line like this. That's going to pivot around that. Like that. Okay. And so we know 0, 0, and 0 at the supports. Okay. And then all we got to do is find that height h. Okay. Okay, and that's going to be h over 14 plus h over 6 is 1. So 6h over 14 times 6 plus 14h over 14 times 6 is 1. So therefore, h is 14 times 6 over 14 plus 6. Okay, which is 4.2. That's going to be 84 over 20. And then we can use slope ratios. And I want you to work this one out to see if you can figure out rise over run and rise over run. But you're going to get a value there of minus 2.4. Is this too hard or is this easy? What do you think?
Pretty easy.
It should be. Like, here's the thing. I want to spend this week learning how to craft the influence lines. Next week, we'll talk about how to use them. So, that's kind of the idea. Let's just worry about making them now. We'll use them next week. That is all I have, everybody.